Hello everyone, this side Ritika, and today we are going to learn about stress strain curve of a mild steel. See, basically stress strain curve tells us about the property of a material, its behavior in different load condition and at different load timing. For example, we want to construct a building. In that case, we cannot use wood instead of steel because wood would be much more weaker as compared to steel. So there are different material which are used at different location according to their property, their characteristics, their behavior under load conditions, right? So before studying stress strain curve for mild steel, we should be aware of some specific terms which are stress, strain, Hooke's law, etc. Now come towards stress. Stress is resistance offered by the body to the deformation. For example, if we have an object in front of us and we are giving an external force on it. So the object tried to oppose that force. So the internal force which is generated to oppose the external force is called stress. Mathematically, it is external force upon area of cross section on which the force is applied. Its unit will be Pascal, and the Pascal is equal to Newton per meter square, where area is meter square. So the unit of stress will be Newton per meter square. Okay, now come to strain. Strain is deformation per unit length in the direction of deformation. Earlier length of object was L. When the force was applied on it, there was a small change in length, that is delta L. So strain will be delta L upon L, that is change in length upon actual length, right? So stress is resistance offered by the body to the deformation, and the strain is deformation per unit length in the direction of deformation, and its unit will be unit of length is meter and change in length is meter and actual length is meter, so it will cancel out. So there is no unit of strain. Strain is unitless, right? This is your stress strain curve for mild steel. Here you can see stress is on y-axis and strain is on x-axis. So there are some points. For example, OA is linear. A is your proportional limit. Proportional limit shows that from O to A at any point stress is directly proportional to strain, and at point A it's your proportional limit, B is your elastic limit, right? Now what is elastic limit? Your elastic limit is value of stress per unit area which body cannot regain its original shape and size. Elastic limit is that point after which further when we increase the load, the shape and size of body cannot regain, right? See, for example, when we stretch a rubber, after a certain value of stretch, it could not regain its shape and size. So the same happened with steel. Now Hooke's law. Hooke's law is when a material is loaded within elastic limit, the stress is directly proportional to strain. Stress is directly proportional to strain. Strain will come under denominator and it would be equal to E, where E is your modulus of elasticity, right? Now come to the figure. So from the curve we can see that Hooke's law is applicable from O to A, where A is your proportional limit. Focus on AD now. Here strain increases more rapidly as compared to stress. This is your stress, this is your strain. You can see from O to A Stress and strain were proportional, that the amount of increase in stress and strain were similar or in the same ratio. But in the curve AD, increase in strain is more as compared to stress. So here in this curve, C is your yield point. C is your upper yield point and D is your lower yield point. Before that, you should know what is yield point. Yield point is the stress beyond which a material becomes plastic. It means that material becomes plastic and it cannot regain its shape. There a point start when there is a permanent deformation gets start in the body. So you can see from here, in that curve, strain increases more rapidly as compared to stress. Upper yield point is, it corresponds to the load reached just before yield point starts. What does yield point? It's a point or it's a value of stress at which the object starts to convert into plastic deformation. Now its lower yield point, it is the load required to maintain the yield. Volume of the specimen increases. Now in the D region we can see, even with the small increase in stress value, there is a large change in strain. You can see from C to D there was a very minute change in stress, but when we reach from D to E at the same stress, the value of strain gets increases from 0.12% to 1.2%. So we can see in the D region, specimen undergoes large deformation with a relatively small increase in applied load. Here deformations are permanent, that they cannot be regained. Volume of the specimen does not change. Ductile material, plastic deformation is more prominent as compared to elastic deformation. So the line simply says that plastic deformation is more considered as compared to elastic deformation. Now come to EF region. As we have seen in the region DE, there was a large deformation. So it was your plastic deformation. When the material reach in the region EF after suffering from DE, it starts to resist the external force which is being occurred on it continuously again. So the material becomes stiff. Because of that, the material undergoes changes in the crystalline structure, resulting in increased resistance of the material to further deformation. So in the simple language we can see, in the region EF, material starts opposing the continuous deformation. Now come to the curve FG. We can see the value of stress is increased to F from E. Right. Now what happened in FG curve? Material has undergone stiffness in the region EF. So when the stress is increased, there is a region called necking. Necking starts occurring in the material. So because of necking, what happened? Diameter of the portion of the specimen begins to decrease because of local instability, and after necking begins, lower loads are sufficient to keep the specimen elongating further until it finally ruptures. See, what happened is, even with the small value of stress, the material is moving towards rupture. When the neck is formed, you can see in your day-to-day life, whenever you have a stick in your hand and because of some reason diameter in between is reduced because of stretching or something else, so even if we apply the small value of force, the stick get ruptured. So the same happen in steel also. After the necking region, the tendency of material becomes more to move towards rupture side, right? We can see from here diameter of the portion of the specimen begins to decrease because of local instability. Lower loads are sufficient to keep the specimen elongating further until it finally ruptures. Rupture along cup and cone shaped surface that forms an angle of 45 degree with the original surface of the specimen start occur. You can see that in this figure cup and cone shapes are formed. So here in the figure, G is your fracture point where the steel finally gets failed. That's all for today. I hope please do like if this video is beneficial for you and subscribe the channel for more videos. Thank you.